So this is the last talk of Hystories projects, and we'll have also a last roundtable. And this is supposed to give you the main conclusions and to draw conclusions, global conclusions from these projects. So I go back to these general charts that I explained on the first day to try to give you an idea of why the project is structured like that and why did we organize all this work package and shows to work on these different items. And I will try to draw conclusions. I will not go again through all the results that have been developed over the last 2 days. I will try to give to put the findings of Hystories into their context, into the state of the art, and also to try to identify what are the gaps that are still there for each of the topics. So first, on the technical maturity of porous underground hydrogen storage. So remember, for the technical development, we were focused on porous hydrogen underground storage. Then to discuss or present the findings of the techno-economic maturity of underground hydrogen storage. So here for both salt cavern and porous media. And so then to come to the implementation plan towards an industrial deployment of underground hydrogen storage. And last, to try to summarize what can Hystories bring to those that are planning and considering deployment at industrial scale of underground hydrogen storage. So about the technical maturity. So the state of the art is that there was no hydrogen storage Europe-wide public information database. There were initiatives like CO2 Stop and ESTMAP mostly, and Hystories based on these works actually. They were not, they've been very useful, and we could not have achieved what was achieved without this basis, but they were not really focused on Hystories. And Hystories introduced and tried to enhance this database collection by adding relevant data, specifically hydrogen relevant, mostly on geochemistry, trying to include information on presence of sulfides, of CO2 in the depleted fields, etc., on the salinity, information that was not necessarily there and looked for when looking mostly at CO2 geological storage. And usually it was not coupled, so it was developed for porous media. It was not really coupled with the databases of salt deposits. So we also brought the two together in the project. And so at the end, we've got this development, so it will be online soon, I guess, Kerry. It's more or less ready to be deployed, and it will be deployed before the end of June. So this GIS that was presented by Kerry will display these 911 traps and salt deposits in a unique place. So that's a progress. Probably there are still gaps. When we look especially at porous media data, it has been developed, but it's still uneven data among countries. There is a lack of data, especially for aquifers. Sometimes there are, depending on the countries, there are more or less proprietary issue to access, notably depleted fields data. Also line rock caverns that are less mature, but that can be a technical options, are not included in this database. So we call for enhancing this data collection at a European scale again, continue working at European scale, and improve the existing works, build on this existing piece of work. So this is the first goal for further action. On the porous media capacity estimations, so state of the art for porous media was that there were some estimations that were published, for instance, by Gas Infrastructure Europe or by the Hystories project, but it was mostly or essentially based on the assumption that all existing underground natural gas storage would be fully converted to hydrogen. So it's a very different approach to the one that was made in Hystories of looking at all potential traps that are there, not only underground natural gas storage. Also, we know it's a capacity estimation can be sensitive if we look at what's been done in closed or closed fields, like estimation of the CO2 geological storage capacity or the shale gas resource. In the last decades, there have been some misestimations that have been made by having a too rough approach, only looking at the geological settings in a very generic way. So we did not really did a detailed study of all of that, but we try to do the best with the available information. And for capacity storage in salt, there was this work published in the reviewed paper by Kaglayan et al. This work that already gave some technical capacity estimation, and we did not develop that further. So main development of Hystories is what Jan presented yesterday. It is this map. So you see each of the 800 or 900 traps, and the size of the dot is a capacity estimation. And it is probably the first time we've got this picture at the European level. So this is, I think, a very interesting tool and data to plan for the deployment of possible underground storage in porous reservoirs. So what are the limits? What can we do to push that further? So limits, I mean, it's based on the database collection that was presented in the slide before, and it kind of inherits all the limits we had first. Then storage performance of porous underground hydrogen storage also would still benefit from industrial reference to see the real impact on the field of mixing due to the fingering, the low viscosity of hydrogen, the heterogeneity of reservoirs. So what does it really? What do we really end up with at the field scale? So we would benefit from field scale porous underground hydrogen storage, and lessons learned from that. And last. So the capacity estimation or the storage resource estimation was done through static models on the 800 or 900 traps. It was the only thing that was feasible in the time we had. It was kind of checked with 22 dynamic models, but it was only done for 22, not for the several hundreds. And this would be required for a better characterization and capacity estimation. Regarding the microbiological risk assessment, so the state of the art here is that it's been discussed for hours over the last 2 days, and it's been discussed in a lot of conferences over the last few years and a lot of peer-reviewed papers. It's probably the most active academic field around hydrogen underground storage today. So there are things that are known, that hydrogen is a very strong reductor, that in abiotic conditions, reaction may not happen below 200 degrees C due to kinetics without bacteria, but it does with microorganisms, and there are microorganisms on the ground. So it has been pictures from this paper from Tyson and co-authors has been already presented twice. So there are like papers that have been quite important over the last few years. A lot of recent developments. So what did Hystories bring compared to the state of the art? So a quite large sampling program, more than 12 sites were sampled. Families of bacteria were characterized. High pressure tests and also low pressure tests were done in contact with hydrogen, with scores from the reservoirs, etc. And we derived first this risk assessment matrix that you see here, that is quite operational. And also we used all these lab results to try to model them. And we did first, and it's really an uneasy, a difficult topic. But we tackled the difficulty of upscaling these lab results to field scale. And this was done through Frixie 0D modeling, then upscale to a reservoir scale with reactive transport codes. So it is probably the big challenge, technical challenge we have today in porous media underground hydrogen storage. It is very highly site specific. So there is a call probably to enlarge the scale of the sampling and characterization that has been done, and to try to test this risk matrix further, and whether it's really the right value, the right parameters. During the roundtable tomorrow, some think that some other parameters should be considered. So maybe this can be challenged as our piece of research. And then there is the fact that this is mostly derived from lab studies. And there is clearly a need for developing models and ways, and not only developing models, but validating models, and validating against observations at field scale. And so this is really probably the big call for further action. Develop pilots or industrial projects that can give feedback, and probably we need more than a few months of pilots. We may need several years or decade of experience to validate models that can be developed to upscale this. About material and corrosion. So wells are the main man-made structure of an underground storage, not considering the surface part. And they're made mostly following standards. It's a very standardized industry. And these standards have been developed by the oil and gas industry, and even by the American one. And it refers to mostly to the American Petroleum Institute standards. And this does not cover hydrogen. So, and hydrogen raises new questions like embrittlement. So I just said these existing standards do not cover hydrogen. There are surface standards, but these are not directly applicable to subsurface conditions. We cannot afford all the recommendations they would make, like over thickness margin, etc. It's not really applicable for well casings. So Hystories, we had this context at the beginning of Hystories. Hystories was a research project on this topic. It developed a quite large material characterization and testing program. It's been presented by Bernd yesterday. I will not go back to it, but over the dozens of steel grades that have been tested, they were then analyzed, and a quite clear recommendation with this final table of the report was made on each of the steel grade about their applicability in a hydrogen environment. So this is a result of a research work. And it was a very extensive, I think, research work regarding the number of grades that have been tested and regarding the number of conditions that have been under which they've been tested. We also benefited a lot from the exchanges with Valorec in the advisory board and the discussion between Geostock and my colleague Cyrian and of course Bernd and Gregor from Leoben, and I think it was quite fruitful, and it probably helped or participated to the move by Valorec, one of the main manufacturers, to kind of clearly propose or recommend a product, one of their products for hydrogen applications. So it's not standardization yet, but it's already quite a very interesting move from one of the main manufacturers to clearly recommend a technical solution. So we call for increasing the number so there is an increasing number of references, but it's still not a standard. So we have to push this towards standardization. And this is only for casings, steel tubes. So we would also need to have the same happen, and it's kind of happening too, but for other well equipments, like well heads, subsurface safety valves, etc. So I will not go through this, but it's partly happening, but we need this to happen also for all the other parts of a well, all well equipments. And last, this from well or well casings or equipment manufacturers mostly target new wells, but gas storage operators have existing wells. And we have to draw and to define a procedure that is supported by rational arguments and that it is accepted to re-qualify existing wells for a hydrogen application. So these were the findings of the first findings, and I mean put in their context of the first part, the technology development of Hystories. We can now move to the second part about the techno-economic findings regarding permitting, readiness, environmental footprint, and public perception. So, state of the art, it's been presented, but it's hard to have a coherent view and a global view of regulation at European scale. Regulation is national, so it was hard to find a view of how ready is regulation in the 27 countries of the EU. That there was a lack of reference data for you're developing a new underground hydrogen storage. What is the carbon footprint? It was hard, probably not feasible to find a public reference giving you a number. And last, the attention of to the public perception. We know from that some close industries like CCS had some difficulties to develop projects. Natural gas storages had probably less difficulties. It's been developed in many countries recently, new storages, even if some were maybe had maybe to go through these questions. So what did Hystories bring? So first, a kind of coherent view based on a survey at the European scale on how ready is regulation at the European scale, yes. Also bring some public references of the environmental footprint of developing a new storage. It's not a judgment; it's more a reference point if you need a value and a vision, and identify how how developing new underground hydrogen storage is seen from the public and from stakeholders. So there are still gaps, of course. We call for further administrative experiment. I mean, it came out in the pilot roundtable also yesterday. Administration is willing to develop this industry, but if it's a first of a kind, you need to involve them, and they're willing. But when it starts getting concrete, you really have to make sure that it's feasible and to engage them in a concrete project, and pilots can help for that. Regarding the environmental footprint, so there is a reference that has been done for underground hydrogen storage, but it should be compared with alternative options. So if you don't do underground hydrogen storage, you would have to do something else to reach net zero. And what would be the footprint in that case? Regarding public perception, the call is for promoting societal information and actions that would help this embeddedness of the public. Regarding the estimation of the optimal underground hydrogen storage in Europe, so on the state of the art, well, first there are some rough, I call it analytical analysis, but maybe the word analysis is too strong of the storage drivers, because I think a lot of you, maybe many of you in the room may have started a research proposal saying that there is a mismatch between energy demand and energy supply, but it's not very concrete behind these words. It's yes, there is this idea that there will be a mismatch, but it's a general idea. You have no idea of the magnitude of this mismatch when you write it just like that, and I did. So this is the state of the art. Also, it's a little bit the same idea, but deployment plans do not always quantify the storage you need. Even if you look at maps, like the European backbone map, I think that will be presented afterwards, there are locations of storages plans, but it's not really linked to a quantification of what is needed in terms of storage capacity. Last, it's all these projections are scenario based. There are a lot of assumptions behind these works. So what did Hystories do? So it's been presented by Christopher. It's this energy model of this modeling of the European energy system, and then in a very economic approach, finding a minimum of a function. Here's the overall cost of the system, and finding the optimum, so the minimum cost, and for this minimum cost, looking at what is the hydrogen storage that is that enables to reach this minimum. So it's been actually a little bit said by your comments right before the lunch, but there is a kind of call for maybe more comprehensive analysis, not only looking at minimizing this overall cost, but also including externalities like societal benefits and also energy independence questions that came out with the Ukraine invasion by Russia and with the Repower EU plan. So there is probably a call for a more comprehensive analysis. And also the analysis has been done, you said that too, at the country scale. And when we look at projects, we find the idea of a regional development at first, hydrogen valleys, and maybe a finer grid, a finer spatial resolution could be helpful to capture that. Next point about cost estimation. So Louis, you said that public sources of underground hydrogen storage that gave capacity-based cost only, euro per megawatt hour. And we never found public sources giving deliverability-based costs. This is a review we did in the, I did in the very good report by IEA TCP. And you see, we try to list all the public sources of underground hydrogen storage costs. And here we find numbers in several works for the capex per energy unit in euro per kilowatt hour. But Hystories is the only project that has proposed also a split between this and the cost per kilowatt. And last, boundaries, what's included in this cost estimation is not always clear. So we developed this cost model in the idea of being hydrogen specific. We did that for both salt and porous media, of being based on a well-defined design with clear boundaries, and in the idea of being parametric. So we chose the parameters that we thought would be relevant to be tuned and that could be useful to adapt to the information and to the site-specific information we can have, the main ones. So this led to this public cost model that can be used and that has these qualities. Gaps. This is still a design-based cost estimate. There is no feedback from industrial scale project of underground hydrogen storage. And probably the biggest gap also in this design-based cost estimate is the estimation of the gas treatment costs, because it has quite high uncertainties in it. Uncertainties because we don't really know the gas composition that will come out from the storage, and we don't also really know the gas composition that will be accepted by the grid specification after the storage. So it's really difficult today to do the cost estimation of this gas treatment part of the storage, and it can actually have a very big impact on the deployment, typically of porous media storage. If the grid specification is to have 99.9% pure hydrogen, it may be difficult. If it's 95%, it may be much more feasible. So it can have a big impact on the deployment of this technology. About the storage market conditions. So there is no practical experience with underground hydrogen storage for net zero objectives today globally. There are experience in other frames from underground for underground energy storage, not hydrogen. Energy, so mostly hydrocarbon storage. Whether it's a business frame that enable storing for geopolitical or strategic reasons, like strategic oil storage, whether it's for seasonality in the demand, mostly for natural gas, whether it's for logistical reasons. So there are some frames that are in place for other business cases, other industries that are very close, but not for hydrogen. So Hystories developed these business cases, try to look at some sensitivity studies to test what would be the most sensitive parameters, but did not really tackle the big gaps we have, which are setting business options to support the first projects, and maybe especially for the strategic objective of underground storage, hydrogen storage. Maybe look at the deployment planning or regulated frames, like it does exist. It's been recalled by Pascal Baylock for oil underground storage this morning. that does exist for that have enabled to develop oil underground, liquid hydrocarbon underground storage. So now I'm getting back to Patrick's questions at the end of this morning. So this is one of the findings of Hystories was a cost, a levelized cost of storage, so the marginal cost of storing underground. So first, and we found values that looked or could look high. It was your understanding, at least. So just to remind, Hystories developed not one cost, but 4 costs. 5 with abandonment, but mostly 4 for both salt and porous media. So the capex was split in 2 parts, euro per megawatt hour and euro per megawatt, and the opex was split in 2 parts, fixed maintenance and variable, related to what is really compressed and spent in electricity for compressing mostly. And it's not one cost that has been used in a World Package 5 energy modeling system. It is these 4 costs. And first, it enabled us to distinguish between the 2 technologies because they don't have the same cost structure. That's why we found the development of both. And it was very interesting actually to find the development of both technologies. It was not an hypothesis. It is a finding of the minimal cost for Europe. And another big finding is that it leads to the storage capacity of 15 to 20% of the annual demand. So it's what you see here. So this is the percentage, the storage as a percentage of the annual hydrogen demand. So the message here, Patrick, is that even if the levelized cost of storage may look high, 1 to 3 euro per kilo, maybe close to what is foreseen for hydrogen production in 2050, green hydrogen, it still is the minimum cost at for the European energy system. And we have to keep in mind that it's only 15 to 20% of the annual demand. So it means that if you consider that your green hydrogen cost will be maybe 2 to 5 euro per kilo in 2050, it is maybe true, but for an electrolyzer that will work, 70% of the time in a year, not 5% or 15% of the time. So it's more not developing storage and developing, for instance, over capacities of green hydrogen production could have been a finding, but it was not. What was found is that 15% of the annual capacity would be 15% of the annual hydrogen production would be hydrogen storage capacity. So at the end, the minimum cost for the European energy system involves having this 15% of hydrogen storage capacity, even with this cost that we found, even with this levelized cost of storage of 1 to 3 euro per kilo, because this cost only applies to 15% of the annual hydrogen production. It does not apply to 100% of the hydrogen production in Europe. And so at the end, it's also one of the results of LBST's reports, but adding this storage adds 15% to the hydrogen supply cost, because mostly it applies to 15% only of the annual production. So now I'm moving to the implementation plan towards an industrial deployment. So we notice that there are high similarities between natural gas and hydrogen storage. And hydrogen storage today is developed a lot by the natural gas storage industry. During the pilot panel session yesterday, it was for natural gas storage operators that were developing and presenting their pilots. So it is, of course, very related and very close. There are some differences. There are physical differences, physical or chemical differences, like the higher reactivity of the hydrogen that is catalyzed by microorganisms, the hydrogen embrittlement in steel, the lower viscosity that can create more fingering effects, etc. So there are these physical differences. There are also other differences when looking at the maturity of the technology. The deployment spatial and time frame are different. If you look at the natural gas infrastructures in Europe, it has developed over centuries. And here you look or you consider developing European infrastructures in a few decades. It's almost nothing for this kind of infrastructures. So it's a totally different time frame. And also it's not the same scale. Now it's a European deployment. It's not a national one anymore. It's also, hydrogen is a developing industry when compared to established industries that have business case running. Here, everyone is looking for business cases. And storage drivers are not that known. They are modeled. They are based on hypotheses. They are identified, but they are not really established. And yes, business cases have to be developed. And last, we're willing to develop this infrastructures in the 2030s, 2050s. The attention to questions like environmental footprint, societal unabandonedness are not the same at what was in place or hundreds of years ago when most other European infrastructure systems were developed. So what is the general idea? So it's hard to summarize everything in two lines, but hydrogen storage in salt caverns has 15 years of experience. It is seen as mature, even if the fact that it's been done 50 years ago does not mean that there's no more technical developments. We did cars, industrial cars 200 years ago, and there are still research ongoing. So it's a continuous process. Some reports like the one published by SMRI that is quite of a good synthesis of the state of the art and the progress that are foreseen. And however, maturity is not only technical. Technical may only be this point, but these three other points here are also very true for salt caverns. For porous media, we don't or didn't identify obvious showstopper for hydrogen underground deployment in depleted fields and aquifers. However, there is still the purity question when withdrawal, the gas treatment cost and the hydrogen grid specifications that could impact this deployment that would still need research and developments. So since we have these differences, we called, we'll not go again through that because it's what I identify in each of the earlier slides. We call for a set of actions that are listed there. And I will go through the my last point briefly. When we reply to the call on implementation was seen as mostly whether or not CHP should push for a pilot. Actually, there are 6 pilots now. It went much faster to what the call had in mind. So it's not really relevant anymore, this implementation. Now, when we discuss implementation, we don't think at a pilot. We think at whether it can be done at the industrial scale. And then we have this chicken and egg problem. One of the most significant issues probably in this. We need 10 years to develop this kind of infrastructures, but we have to decide it now if the demand wants it to be ready in 10 years. So hopefully there are some people that are developing visions to help have a clear idea of when do we need to start these deployments. So natural gas TSOs through the hydrogen, European hydrogen backbone, gas industry, including DSOs in general, with this hydrogen infrastructure map, and the overall hydrogen industry, let's say, with these maps with hydrogen corridors to make it simple. So the idea is, what can Hystories bring to these people looking at deployment at industrial scale? So I think we can bring analysis at a European scale, because all these three examples we're looking at the European scale, and that's probably the right scale for these questions today. So we gave a capacity volume demand per country. So it's the same. It's also a pan-European analysis. So when we restricted the storage capacity in Italy to what was physically identified, so we went from here to here, and it was presented by Christopher. Then it increases the storage in another country, France. So it's really a pan-European analysis that has been done. So we identified, I will go quickly, that there is enough capacity in porous media. And we identified also, we gave costs that are site-specific and cycle-specific, even if it's high level. And last, this information, something is missing to help people. It's where are these traps? Because it's local opportunities, these hydrogen valleys. So that's why we developed this geographical information system of this cost and suitability data. So you can find that on our website, hystories.eu/map, and you can zoom and play around. You will find back the European backbone, hydrogen backbone network that was kindly provided. The salt deposits too, that was kindly authorized by SMRI, and Hystories work that has been the development of this porous media database, and then the estimation of these costs for fast and seasonal cycles, and of this suitability mark. So this enabled to capture also the local dimension and local opportunity that is important for developing these projects. So that's it.